back, starting another chapter on control flow. The plan is to get through conditional logic, conditional execution. So we'll stop at around this while loops part. That's the goal. We'll get through section 9.3. So we'll start off by just reading the chapter here. Control flow. Logic, like whiskey, loses its beneficial effect when taken in too large quantities. Edward John Morton Drax Plunkett, Lord Dunsany. Compared to last chapter's grueling marathon, today is a light-hearted frolic through a daisy meadow. But while the work is easy, the reward is surprisingly large. I'm just going to close the door here. Right now, our interpreter is little more than a calculator. A LOX program can only do a fixed amount of work before completing. To make it run twice as long, you have to make the source code twice as lengthy. We're about to fix that. In this chapter, our interpreter takes a big step towards a programming language major leagues. Turing completeness. Turing machines, briefly. In the early part of last century, mathematicians stumbled into a series of confusing paradoxes that led them to doubt the stability of the foundation they had built their work upon. To address that crisis, they went back to square one. Starting from a handful of axioms, logic, and set theory, they hoped to rebuild mathematics on top of an impervious foundation. They wanted to rigorously answer questions like, can all true statements be proven? Can we compute all functions that we can define? Or even the more general question, what do we mean when we claim a function is computable? They presumed the answer to the first two questions would be yes. All that remained was to prove it. It turns out that the answer to both is no, and astonishingly, the two questions are deeply intertwined. This is a fascinating corner of mathematics that touches fundamental questions about what brains are able to do and how the universe works. I can't do it justice here. The most famous is Russell's paradox. Initially, set theory allowed you to define any sort of set. If you could describe it in English, it was valid. Naturally, given mathematicians' predilection, not sure what that word means, for self-reference, sets can contain other sets. So Russell, rascal that he was, came up with R is a set of all sets that do not contain themselves. Does R contain itself? If it doesn't, then according to the second half of the definition it should. But if it does, then it can no longer meet the definition. Cue mind exploding. What I do want to note is that in the process of proving that the answer to the first two questions is no, Alan Turing and Alonzo Church devised a precise answer to the last question, a definition of what kinds of functions are computable. They each crafted a tiny system with a minimum set of machinery that is still powerful enough to compute any of a very large class of functions. They prove the answer to the first question is no by showing that the function that returns the truth value of a given statement is not a computable one. These are now considered the computable functions. Turing's system is called a Turing machine. Church's is the lambda calculus. Both are still widely used as a basis for models of computation, and in fact, many modern functional programming languages use the lambda calculus as their core. Turing called his inventions A-machines for automatic. He wasn't so self-aggrandizing as to put his own name on them. Later, mathematicians did that for him. That's how you get famous while still retaining some modesty. Turing machines have better name recognition. There's no Hollywood film about Alonzo Church yet. But the two formalisms are equivalent in power. In fact, any programming language with some minimal level of expressiveness is powerful enough to compute any computable function. You can prove that by writing a simulator for a Turing machine in your language. Since Turing proved his machine can compute any computable function, by extension, that means your language can too. All you need to do is translate the function into a Turing machine and then run that on your simulator. If your language is expressive enough to do that, it's considered Turing complete. Turing machines are pretty dang simple, so it doesn't take much power to do this. You basically need arithmetic, a little control flow, and the ability to allocate and use theoretically arbitrary amounts of memory. We've got the first. By the end of this chapter, we'll have the second. We almost have the third too. You can create and concatenate strings of arbitrary size, so you can store unbounded memory, but we don't have any way to access parts of a string. Conditional execution. Enough history, let's jazz up our language. We can divide control flow roughly into two kinds. Conditional or branching control flow is used to not execute some piece of code. Imperatively, you can think of it as jumping ahead over a region of code. Looping control flow executes a chunk of code more than once. It jumps back so that you can do something again. Since you don't usually want infinite loops, it typically has some conditional logic to know when to stop looping as well. Branching is simpler, so we'll start there. C-derived languages have two main conditional execution features, the if statement and the perspicaciously named conditional operator, or sometimes called the ternary operator. An if statement lets you conditionally execute statements, and the conditional operator lets you conditionally execute expressions. The conditional operator is also called the ternary operator because it's the only operator in C that takes 3 operands. For simplicity's sake, LOX doesn't have a conditional operator, so let's get our if statement on. Our statement grabber gets a new production. The semicolons in the rules aren't quoted, which means they are not part of the grammar meta syntax, not LOX's syntax. A block does not have a semicolon at the end, and an if statement doesn't either, unless the then or else statement happens to be one that ends in a semicolon. Okay, so let's extend our parser to handle this grammar now. Okay, so our statement can now either be an expression statement, which is this one, if statement, a print statement, or a block. So now we just need to add the if statement. So if statement is if followed by open and close parentheses containing an expression, a statement, and then possibly an else statement. That semicolon's not part of it. Okay. So let's see if that's too large to do inline. If so, we can define that somewhere else. We'll say if left parentheses conditional expression right parentheses. Yeah, let's move this out. So we'll do if statement, and that will just equal if left parentheses else. Actually, I like how that's done there because there's probably a way of saying like conditionally some part, but there we go. That's good right there. Okay. Let's see. What else do we need to do here? Okay, so if statement, left parentheses containing an expression, which is the conditional, the statement itself. Is that how they have this here? Statement, yes. That statement could be any of the things, including another if statement, expression statement, print statement, or a block. Okay. Else, and then another statement. And then we make an if statement, CTE, CT block statement, which is blank. Okay. Now we have to actually have that in the AST. Now these are all creating statements in declaration. Sorry, in expression statement, print statement, block statement. Okay. So let's now do a if statement in here. Of expression, statement, statement. That looks right. Cool. All right. Let's see if we can run the program. Okay, we ran into an issue already. Oh, okay. It's because we're not actually handling that yet in the eval and in the print. Let's move on and see how we are going to handle this in the future. An if statement has an expression for the condition, then a statement to execute if the condition is truthy. Optionally, it may also have an else keyword and a statement to execute if the condition is falsy. The syntax tree node has fields for each of these 3 pieces. Like other statements, the parser recognizes an if statement by the leading if keyword. Okay, when it finds one, it calls this new method to parse the rest. So again, we don't really have to write all this code because that's all taken for us by the parser men here. The parentheses around the conditions are only half useful. You need some kind of delimiter between the condition and the then statement, otherwise the parser can't tell when it has reached the end of the condition expression. But the opening parentheses after if doesn't do anything useful. Dennis Ritchie put it there so he could use the closing parentheses as the ending delimiter without having unbalanced parentheses. Other languages like Lua and some basics use a keyword like then as the ending delimiter and don't have anything before the condition. Go and Swift instead require the statement to be a braced block. That lets them use the opening squiggly at the beginning of the statement to tell when the condition is done. As usual, the parsing code hews closely to the grammar. It detects an else clause by looking for the preceding else keyword. If there isn't one, the else branch field in the syntax tree is null. That seemingly innocuous optional else has, in fact, opened up an ambiguity in our grammar. Consider if first, if second, when true, else when false. Here's a riddle: which if statement does that else clause belong to? This isn't just a theoretical question about how we notate our grammar, it actually affects how the code executes. If we attach the else to the first if statement, then when false is called, if first is falsy, regardless of what value second has. If we attach it to the second if statement, then when false is only called if first is truthy and second is falsy. Since else clauses are optional and there is no explicit delimiter marking the end of an if statement, the grammar is ambiguous when you nest ifs in this way. This classic pitfall of syntax is called the dangling else problem. Here, formatting highlights the two ways else could be parsed, but note that since whitespace characters are ignored by the parser, this is only a guide to the human reader. So it is possible to define a context-free grammar that avoids the ambiguity directly, but it requires splitting most of the statement rules into pairs, one that allows an if with an else and one that doesn't. It's annoying. Is that what we're doing in this? We're splitting it into two different rules, one that has an else and one that doesn't. Not sure. Instead, most languages and parsers avoid the problem in an ad hoc way. No matter what hack they use to get themselves out of trouble, they always choose the same interpretation. The else is bound to the nearest if that precedes it. Our parser conveniently does that already. Since if statement eagerly looks for an else before returning, the innermost call to the nested series will claim the else clause for itself before returning to the outer if statements. Syntax in hand, we are ready to interpret. So hopefully that's what's going on here too, but we can test that out. All right, so then the implementation of the evaluators here. Visit if statement, statement if is truthy, evaluate condition, execute statement.then branch, else if statement.else branch, execute. Okay. The interpreter implementation is a thin wrapper around the self-same Java code. It evaluates the condition. If truthy, it executes the then branch. Otherwise, if there is an else branch, it executes that. If you compare this code to how the interpreter handles other syntax we've implemented, the part that makes control flow special is that Java if statement. Most other syntax trees always evaluate their subtrees. Here, we may not evaluate the then or else statement. If either of those has a side effect, the choice not to evaluate it becomes user visible. Okay, let's implement this now. Let's go to eval. And we're now evaluating statement. And there's going to be a if statement. And if statement has C, T, and F, true or false. That's not what we used in the parser. We used true and E for else. I kind of like the F there. That's not what I want to do. This will be F and F there. Okay. All right, true, false, and then let's see. If eval expression scope C, take the condition and evaluate the expression, equals literal boolean true, then eval statement scope T. Else, oh, there's a match F with some, no, we don't need all that. So we're just going to eval statement scope F and get rid of that. Okay, that looks fine. Print now needs to have, I guess nothing there. Print AST is where it was complaining here. We'll do if statement print statement S1, print string, print statement S2. Oh, so now I need to make this recursive. Okay. Is eval's already recursive, so we're good on that. Okay, so I must have changed something in the parser. Two productions that share semantic action must define exactly the same identifiers. Here, E is defined in one production, but not in all of them. Ooh, interesting. Exactly the same identifiers. Here, E is defined in one production, but not in all of them. Line 72. Two productions that share a semantic action must define exactly the same identifiers. This is saying on line 72, characters 11 through 12, which is right here. I was expecting it to be complaining about something up here. For now, what I'm going to do is I'm going to remove this block and see if that does anything. It does not. So let's try moving this thing in line. And remove this. Okay, it's fine with that. So let's maybe move the else one in line as well. Okay, it's good with that too. All right, I don't know if they don't have any like test code for this yet. But we can just write out some test code here. See if it's working. Actually, you know what? Let's try it with, yeah, this bit of code with that dangling else issue. Okay. So we'll say if one, actually let's do something a little bit more featured, fully featured here. We'll say var a is equal to 1, var b is equal to 2. We'll say if a, oh actually we don't even have conditional comparators yet, do we? Okay, yeah, so that's okay. We can just say if true, if false, and then we'll say print true, else print false. Okay, let's give that a try. Okay, so we got false, which meant that, okay, so if true, this must have been true there. So then it continued on to say, if false, print true. So if I were to make that true, we should get true, right? If I were to make this one false, it basically doesn't do anything, right? Because there's no else block to this first one. The else block is only on the second one here. So if we make this one true and then that one false, that's when we get the actual false printed out. Perfect. That's working out great. All right, let's move on to logical operators. Since we don't have the conditional operator, you might think we're done with branching, but no. Even without the ternary operator, there are two other operators that are technically control flow constructs, the logical operators and or. Actually, you know what? I think we did implement A equals 1, and we'll say B equals 2. Nice, okay. So A equals 1 and B equals 2, so therefore true is printed out. Cool. These aren't like other binary operators because they short circuit. If after evaluating the left operand we know what the result of the logical expression must be, we don't evaluate the right operand, for example, false and side effect. For an and expression to evaluate to something truthy, both operands must be truthy. We can see as soon as we evaluate the left false operand that that isn't going to be the case. So there's no need to evaluate side effect and it gets skipped. This is why we implemented the logical operators with other binary operators. Now we're ready. Oh, sorry, we didn't implement the logical operator with the other binary operators. The two new operators are low in the precedence table, similar to OR and AND, and C. They have their own precedence with OR lower than AND. We slot them right between assignment and equality. I've always wondered why they don't have the same precedence like the various comparison or equality operators do. Okay, so here we got, there is some way of defining precedence and such in the parser here, but truthfully I'm not really sure how that's working. Or if it's working even. Anyway, we'll continue on. So now we have an expression as an assignment. Where's our assignment? Right there. Assignment, identifier equals assignment, logic or, logic and, or logic and, logic and equality. Okay. So this is actually now referring to some grammar thing that I didn't understand in the last chapter. This equality thing came out of nowhere and I don't know what it means. They're doing this in, we slot them between assignment and equality. Assignment cascades to logic or. We could reuse the existing expression binary class for these two new expressions since they have the same fields, but then visit binary expression would have to check to see if the operator is one of the logical operators and use a different code path to handle the short circuiting. I think it's cleaner to define a new class for these operators so they get their own visit method. Okay. All right, so let's think about how we want this to be done. Essentially, all you're having is an expression on either side of an and or an or. So we'll say L equals expression. We'll do and. Something like that. And there's this new thing called logical, which we don't have. So now we need to add that to AST. That's in the expression part. And then op now needs to have and or added to it. We have this thing called control instead. I don't know when I started implementing that. That's kind of interesting. So logical control. I think I want to stick with this logical thing. I'm going to remove that control thing there. And we're just going to add and in order to that. Okay. That's kind of be a lot of things that we have to change now for that. Okay. So now we need to update our eval here. I got to get rid of this control thing and then add a logical thing here. Let's do a let eval logical be literal boolean L or literal boolean R. These are not necessarily literals, these are expressions, right? Yeah. So I don't really care about these being, I could just make that L and R. L and R. So what's going on with this and? This variant pattern is expected to have type control. There is no constructor and within OCaml.ast.control. I think that's just the tooling catching up with stuff. I think after I save stuff and compile, we'll get better on that. So this will now be eval logical, and I suppose we need to pass scope as well. Scope and eval logical scope. Eval expression scope L. No, we don't want to eval the expression yet. We want to just pass it along without evaluating it. I guess we could always evaluate the left side, right? We can eval expression scope left, and then we can just pass R over. Okay, let's compile this thing so that we get some better, more correct warnings here. Okay. So eval logical scope. If I remove this one, some things are better now. We want to make sure that we maintain this type signature here. String expression hash table t scope expression. Actually, I think we can even do something like eval expression type or something like that. Is that not a thing? I don't know. It's okay. We just want to maintain that type signature. Okay. So now if I uncomment this out, we end up having a bool being replaced with this expression here and returns back a bool. That shouldn't be the case. And I think it's because this one is messing things up here. So we should say if the left side is true, then we just return the left side, right? Something like that. Else, it's not literal R. This is an expression again. And then this one should be R. Okay, now I'm going to need to eval expression in here, which means now this needs to be an and. Let extension with punning expected. So this should be eval expression scope R, something along those lines. Oh, you know what? I think I can do better than this. I can move this. I can make this a let and put the and below it. There we go. So now, in the case where L is true, we have to evaluate the right side in order to figure out what to do, right? So, okay, so for or, if the left side is true, then we return the left side. Else we evaluate the right side and we return that. For and, if the left side is false, then we return the left side. Else evaluate. Yeah, that looks correct. Okay. That looks pretty good. Unbound value print. Not sure what's going on with that. Why it's starting to have issues with print there. Probably because print is now missing some stuff. There is no constructor control within type expression. Okay, yeah, so print is now needs to be updated. We don't need this print control thing. We don't need this one either. We now need to have a logical. And or there we go. Okay. Print AST. Okay. Almost chased down all the issues here. Okay, now we just need up here, logical, sure, good enough. Okay, print AST is still not happy. Oh, because this one is now having an issue. And, or, and then we can remove the print control. Okay. Hey, there we go. We're back to back to where we needed to be. All right. To weave a new expressions into a parser, we first change the parsing code for assignment to call OR. The code to parse a series of OR expression mirrors other binary operators. Its operands are the next higher level of precedence, the new AND expression. That calls equality for its operands, and with that, the expression parser is all tied back together again. We're ready to interpret. Okay. If you compare this to the earlier chapter's visit binary expression method, you can see the difference. Here we evaluate the left operand first. We look at its value to see if it can short circuit. If not, and only then, do we evaluate the right operand. The other interesting piece here is deciding what actual value to return. Since LOX is dynamically typed, we allow operands of any type to use truthiness to determine what each operand represents. We apply similar reasoning to the result. Instead of promising to literally return true or false, a logic operator merely guarantees it will return a value with appropriate truthiness. Fortunately, we have values with proper truthiness right at hand, the results of the operands themselves. So we use those. For example, print high or 2 prints high. Print nil or yes, yes. On the first line, high is truthy, so the OR short circuits and returns that. On the second line, nil is falsy, so evaluates and returns the second operand, yes. That covers all the branching primitives and locks. We're ready to jump ahead to loops. You see what I did there? Jump ahead, get it? See? It's like a reference to I'll forget it. So let's see if this actually works. I don't think I actually implemented truthy and falsy. Oh, I think I did actually. So high or 2 print, oh, it printed 2. Nil or yes printed yes. So my truthiness is not correctly defined. You can see where that is being defined, I suppose. Oh yeah, it's somewhere in the longs of when we do let me think about this. So when we actually evaluate, oh, okay, that's what it is. So here, when we're evaluating this logical, we say it has to be exactly Boolean true, right? So if I were to make this one now true or 2, it should be true. If I do false or 2, I should get a 2, right? Nil or yes. So if I make that true, then I get true. Okay. So I'm not correctly implementing truthiness and falsiness. I'll add that to the list of things that I gotta fix in here. But we got through conditional stuff, and next time we'll pick back up in loops. So see you next time.